Welcome to the Deep Dive. We're your shortcut to getting up to speed on, well, really fascinating topics. Today, we're jumping into the world of combinatorics, specifically an interesting sequence from the online encyclopedia of integer sequences. It's OEIS A000273. Now, for you listening, maybe especially if you're a number 30 student, this deep dive, it's all about getting those aha moments. We're talking about a specific thing, unlabeled, simple digraphs with endnodes. Our goal is to unpack what these actually are, why counting them is, well, surprisingly complicated, and maybe how these abstract ideas link up with other things. Ready?
It really is quite beautiful, mathematically speaking, how counting something like graphs can get so complex and so useful. These are foundational ideas.
Absolutely. So let's start with the basics. When we say digraph, what exactly is that?
Right. So a directed graph or digraph, it's essentially a set of vertices. You can think of them as points or nodes. And these nodes are connected by directed edges, sometimes called arcs or arrows. The really key part here compared to a regular graph is that these connections have a direction. They're ordered pairs, meaning an arc goes from a specific tail vertex to a specific head vertex. That directionality, it's crucial. It dictates flow.
Got it. So A to B is distinct from D to A. Makes sense. Now the sequence, A000273, it specifically mentions simple digraphs. What does the simple part add?
Simple is an important filter here. It cleans things up a bit. A simple directed graph means, first, no loops. So no arrows starting and ending at the same vertex.
Okay.
And second, no multiple arrows going between the exact same two vertices in the same direction. If you allowed those things, you'd have what are called directed multigraphs, or maybe loop digraphs, different objects. So simple really focuses us on the core connections between distinct pairs of nodes, one way at most.
That clears it up. But then there's this other word, unlabeled. That seems to be where the real counting challenge comes in. Why does unlabeled make things so much harder?
Yes. This is where combinatorial counting gets really interesting and, well, difficult. When we talk about unlabeled graphs, we stop caring about the specific names or labels we might put on the vertices. Instead, we're counting distinct structures, structural patterns.
Like unique shapes.
Exactly. Think of it maybe like snowflakes. You can talk about different types of snowflake structures, right? Their overall shape. Even if the individual water molecules are different and similar here, if two graphs have the same connection pattern, if you could sort of pick one up and rotate it or rearrange its nodes without breaking connections and make it look identical to the other, then they count as the same unlabeled graph. Even if vertex 1 in the first graph corresponds to vertex 5 in the second graph, the labels don't matter.
I see.
Mathematically, we say we're counting non-isomorphic graphs. And that's much, much harder than counting labeled graphs where every different labeling counts as distinct. You have to wrestle with symmetry.
That snowflake analogy helps. Unique structures, not unique labels. And you really see the scale of this challenge when you look at the actual numbers in the sequence. A000273, for n equals 0, 1, 2, 3, 4, 5, 6. It goes 1, 1, 3, 16, 2, 18, 900, 608. And then wait for it, 1,540,944. And the sequence notes say the off-F set is 0, 3, meaning that first one is for any real nodes. The growth is just incredible.
It is. It's a classic example of what we call a combinatorial explosion. Even for a small number of nodes, like any 6, the number of possible distinct structures just skyrockets. It really underscores the difficulty. It's not just a casual counting exercise. There's an asymptotic formula. McElroy found it back in 1955. It gives an approximation for AN.
Approximation.
Yeah, it says AN is roughly 2 to the power of n times n1, all divided by n factorial. Just looking at that formula, 2n gives you a sense of the scale and the kind of mathematics involved. It tells us these numbers get huge fast, too fast for exact counting by hand very quickly.
Right. So with numbers ballooning like that, this clearly isn't something you just figure out on a napkin. What kind of computational tools or clever math is needed to actually calculate these terms beyond the first few? The OEIS page mentions things like Maple, Mathematica, PARI, Python code.
You're absolutely right. Beyond very small n, you need serious help. Specialized algorithms, powerful software, the code examples you see mentioned, they often rely on quite advanced techniques. Things from group theory, actually, like Burnside's lemma or maybe the Pólya enumeration theorem. These are sophisticated mathematical tools.
Tools for what exactly?
Well, they provide a systematic way to count structures while automatically accounting for symmetries. Remember how we said unlabels means ignoring symmetries? These theorems give you a mathematical framework to do precisely that. They let you count the distinct patterns by essentially dividing out the redundancies caused by symmetry. It turns an impossible brute force check into something, well, still complex, but manageable computationally. Clever stuff.
Very clever. Using the symmetry itself to simplify the counting. Okay, so stepping back a bit, what's the bigger picture here? How does this specific sequence, A000273, fit into, the wider world of math or even other fields?
It's a really core example in an area called graphical enumeration, which is a big part of combinatorics. The OEIS entry links to standard references like the CRC Handbook of Combinatorial Designs or Hurry and Palmer's book Graphical Enumeration,
Yeah.
foundational texts. But it's not just pure theory. These ideas pop up in surprising places. The source material mentions connections to things like genetic algorithms, maybe modeling gene interactions,
Interesting.
or index coding in information theory, optimizing data transmission by understanding the structure of information flow. Even things like leader election in computer networks, designing protocols for distributed systems. It shows how these abstract mathematical structures, these digraphs, can actually model very real-world complex processes.
That really bridges the gap from abstract math to practical application. Are there other related concepts tied to digraphs that maybe our listeners who are getting into number theory or related areas should be aware of, things that often come up?
Oh, absolutely.
Yeah.
When you start working with digraphs, several other important properties emerge. You'll hear about in degree and out degree of a vertex. That's just the number of arrows pointing in versus pointing out.
Okay.
Vertices with 0 in degree, nothing pointing in, are called sources. They only send stuff out.
Mm-hmm.
And vertices with 0 out degree, nothing pointing out, are sinks. They only receive. And then there's connectivity. Is the graph connected? For digraphs, it's a bit more nuanced.
Awesome.
Well, you can talk about weakly connected. That just means if you ignore the arrow directions, the underlying graph would be connected. But there's also strongly connected, which is stricter. It means you can get from any vertex to any other vertex by following the directed arrows. These properties, in degree, out degree, sources, sinks, connectivity, they're all fundamental for analyzing whatever system the digraph is modeling. How information or influence flows, where it starts, where it ends up.
Right. So we've gone from the basic idea of a directed graph, added the simple constraint, tackled the tricky unlabeled aspect, and seen how the sheer number of these structures explodes. And we've touched on the sophisticated math and computing needed to count them, plus their surprising connections elsewhere.
Exactly. It's a great example of the depth and elegance you find in combinatorics, and how abstract counting can have very concrete relevance.
So here's something to think about as we wrap up. We've seen this exponential growth as our ability to compute gets even better, allowing us to calculate terms for much larger n. What might we discover? What new kinds of complex systems, maybe in biology, maybe AI, maybe something else entirely, could these incredibly numerous and intricate, unlabeled, simple digraphs help us model or understand? What insights are waiting out there in those larger numbers?